Hello, my name is Darren Thomas, and I am the Director of Educational Research Techniques. We're now in Unit 2, Lesson 4. And what we're going to do in this video is we're going to do our model testing for the numeric decision tree we created in the previous video. So let's go ahead and move over to RStudio, So you can see this is the decision tree that we made last time. And now what we're going to do is we're going to take this model that we have right here and use it for predicting the outcome for data from our testing set. So we're going to set our seed again. Remember, if you've closed RStudio since the last video, you need to run the packages again to make sure everything is there. Sometimes that's necessary. Now in line 2, we're going to do with the predictions here. So basically I'm using the predict function, and I'm going to use my model that I made in the last video, PSID_model, and I'm going to use the testing data, PSID_test. I press Control Enter, and if you're bored, you can look at it. Let's just do that real quick. And you can see right here, these are the predictions for how many kids someone's going to have based on the model we've created. And so you can see the values are rather redundant: 2.4, 2.46, 0.735, etc., all like that. So that's it. Now here's what we do. One way to figure out how accurate your model is to compare the summary statistics of the predictions with the actual values of the test set. If the numbers are similar, it means that the prediction is doing a reasonable job. And this is something that is unique when you're doing numeric prediction. So I'm going to use the summary function. I don't need to see the plot as much. I need more space to take a look at the summary function output. So this is the summary function output for the prediction value. So the mean is about 2.2. You can see the minimum, the maximum, the interquartile range, etc. Now, if we compare that with the summary statistics for the number of kids in the test set, we get the following. So you can see here they line up pretty good. So let's see here. The minimum is a problem. They always predicted that someone have at least 0.7 kids or 1 kid or whatever. The first quartile is very accurate. The mean the median is a little bit off here. You can see the difference between 2.4 and 2.0. The mean is not bad. Our test set expects the average person to have 2.5 kids, whereas we predicted 2.2. I mean, it depends on what your concerns are. And then also you can see here the third quartile is 2.4 here and 3. Again, a little bit more off. And then in the last one, we get 2.7, but in the test set, somebody had as many as 10 kids. Now, in the real world, you would probably remove somebody from the test set if they had 10 kids. That's considered more of an outlier experience in the current day. Now, another technique, and this doesn't work as well for our particular example because, in case you don't know, kids is kind of a count variable, and the distribution for count data is different with normal distribution. But if you're using something that's more of a continuous variable in terms that it has a normal distribution, calculating the correlation can be very valuable. So here in line 5, I'm making a correlation between the prediction values and the actual number of kids in the test set. That's what line number 5 is telling me. And the correlation here is 0.31. Now this would be often considered a red flag in most statistical analysis when you're trying to compare the training in the test set or the test set with the predictions that you have. This would be considered a problem. However, again, like I just mentioned, children, the number of kids a person has is considered count data, and it does not follow a normal distribution, so we're going to forgive that. But please keep in mind this may be useful if your data is normal. And remember that one of the powers of decision trees is that they're very good or robust against data that is not normal. For example, dealing with an output, a y variable that is definitely count data and not normally distributed. Now in line 7, 8, and 9, we are making a function here to find the mean absolute error. The mean absolute error just tells you the amount of error that is inside the data set. And basically we're just making a function. There are definitely packages available that will do this for you, but this is what we did in this example. So I'm making a function called MAE, which stands for mean absolute error. And inside the function there are 2 arguments, actual and predicted. And so what I'm doing is that I'm going to find the mean of the absolute value when I subtract the actual from the predicted. That's what I'm doing. So I'm going to go ahead and run this. And so now I'm going to calculate the mean absolute error. So my actual values are I guess this is actually backwards, huh? I should probably remove that. Okay, so what we need to do here is as follows. What we're doing here is we're taking our actual value, which is p-test kids, and our predicted value ps underscore pred. So we're going to find out what the mean absolute error is here. 1.13. You can see the answer right there. Now we're going to find the average for the kids in the training set. So the average. Now what are we trying to do here? We're going to compare the mean absolute errors between what we got in when we did the prediction and also what is actually in the test set when we look at the kids, the number of kids, and we want to compare it to when we subtract the mean from what we expect in the in the test set. So if these values are about the same, then we know that our model is doing okay. So let me just go back and explain again. In line 11, we found the mean absolute hour when we compared the actual number of kids in the test set with the predicted kids for each row. It sums it up and finds the value for that, the mean for that. Now in line 12, we just found the average number of kids in the training set. That's what we're doing here. And in line 13, we're trying to compare the average number of kids in the training set with the average number of kids in the in the test set. And if these numbers are about the same, we're doing okay. So let me go ahead and run this, run this, run this. And so you can see here that 1.17 and 1.13 are about the same. So that indicates that our model is not really improving things that much. We would expect the error to be lower in the test set because are somewhere equivalent, if not equal to or lower. In other words, that our model is doing okay. So we're in the same range, but nothing amazing to get excited about. So this is kind of what's happening in this particular video right here, is that we were able to test our model using the test data and to look at the various metrics. So the metrics that involved were the summary statistics, seeing if they're the same, calculating the correlation, which I gave you a little warning message about that, and also the mean absolute error, which should hopefully either be about the same, but not extremely worse, or maybe also if it's really better, something weird is going on too, because normally you perform worse on the test data because the model does not know that data yet. So my name is Darren Thomas. I hope this video was useful for you. I'm the Director of Educational Research Techniques. We'll see you in the next video when we look at modal trees.